Dr. Sarah Guerin, who is our second speaker, was graduated with BSc in applied physics. Then she completed her PhD in 2018 in piezoelectric modeling with Damien Thompson. Her postdoctoral research was carried out in the modeling team of the Science Foundation Ireland Research Centre for Pharmaceuticals, SSPC, in which she is now funded investigator. She now runs her research group, the Actuate Lab in the Department of Chemical Sciences, and the Bernal Institute in the University of Limerick, Ireland. She has been awarded more than €2.5 million grants to work on both in silico and ex silico engineering of biomolecular crystals, primarily for the application areas in eco-friendly sensing and pharmaceuticals. She currently works with a large number of international research groups as a world leader in computationally predicting the electromechanical properties of novel molecular crystals. She's been awarded the British Association of Crystal Grow Young Scientist of the Year Award and is the 2023 Research Ireland Early Career Researcher of the Year. Congratulations on these achievements. And Sarah, the screen is yours.
Thank you so much. Thank you for the invitation, and thank you to Sujesh for absolutely setting up this talk very nicely with some of those last comments. So my goal today, I suppose, is to take you through kind of the last 6 years of our development of organic molecular crystals, mainly for piezoelectric applications, and then to preview some of the cool new things that we're working on currently in 2024. So, yeah. So our group is the Actuate Lab. So you can see most of them there on the left-hand side. You'll see when people show pictures of Ireland, they tend to be lovely, sunny scenes of beaches and mountains. But I said I'd give you a realistic picture of what the west coast of Ireland looks like, which is still this very beautiful but very stormy place that we're at over on what's called the Wild Atlantic Way. On the west coast of Ireland in Limerick. So our group spans 3, I suppose, pillars, where we have our molecular modelers, and then we have our experimental crystallography team, and then our device engineering team. So these 2 groups are working together to screen, discover, engineer in terms of how we know it as crystal engineers, and then literally mechanical and electrical engineering to get our materials into functioning devices for technological applications. So just to introduce piezoelectricity briefly for anybody who mightn't be working in that area, piezoelectricity comes from the Greek meaning to press. That comes from what we call the direct piezoelectric effect, which is on the left-hand side here. So when you apply a force, the material will generate a charge. And then we also have the converse piezoelectric effect, where for the same material, if you apply an electric field through it, it will start to strain and distort. So the direct effect would be for sensing applications, and then the converse effect would be for actuating applications. So broadly speaking, we say that these materials interconvert mechanical and electrical energy, but something that I always like to highlight specifically for our main application is that it's a linear electromechanical coupling, which means the more force that you can apply to a material, the more useful voltage or electricity you're going to get out of it. So that's really exciting for us as crystal engineers, because if we go towards looking towards a more flexible molecular crystals, we can get much more voltage out of those materials because of their flexibility and the amount of force that we can apply to them without them breaking or going towards that fracture limit. So in terms of applications, the main thing that our group targets is what's known as energy harvesting. So energy harvesting is when your piezoelectric material is detecting either direct or ambient mechanical stimuli in the environment around you, and then using that to power low power everyday consumer electronics. So Coldplay have been doing some great promo for me in the last couple of years and my research, and a number of nightclubs have also started using these piezoelectric tiles in London and Singapore. So the way that this works is that you can embed an array of your piezoelectric crystalline materials into these, they call them kinetic dance floors, that's the commercial name, and every step will generate a pulse of electricity that can be stored in a capacitor and then be used to power devices. So you can see those people there at Coldplay generating electricity and severely reducing the environmental impact of these kinds of events. So that sounds great, and that seems to be working great for Coldplay. So what's the issue with piezoelectrics, or why are we working on this? So the elephant in the room with piezoelectric materials is that the two most dominant commercial applications, so for rigid piezoelectrics, we use PZT, which is a lead-based ceramic. For flexible applications, we use a fluorinated polymer called PVDF. So such a diverse, there's billions of piezoelectric sensors around the world, but very not environmentally friendly materials are being used. So it's a really fun challenge for us as crystal engineers, because we now have a class of materials where we don't have to choose between a rigid application and a flexible application, because we know we can engineer our crystals with our structure property relationships to fill the spectrum of piezoelectric applications and hopefully start to phase out these environmentally damaging materials that are currently in use. So the main project in our group, this is our ERC starting grant, is called PB-Free. So piezoelectric biomolecules for lead-free, reliable, eco-friendly electronics. So when you look at the current alternatives in the ceramics field for piezoelectric applications, you see that they're lead-free, which sounds very environmentally friendly, but those lead-free alternatives contain bismuths, they contain niobium, they contain a number of other elements that do, if you actually look into the research, do even more damage to the environment in terms of being dug out of the ground, in terms of leachables, in terms of all of those things. So we're proposing molecular crystals as a new material class for piezoelectric applications, where we can embed the properties that we need for a specific application using crystal engineering principles. So that's what we're currently working on. In terms of the history of this field and kind of biopiezoelectrics as a whole, it was the 1950s that Professor Fukuda first discovered that our bone, our tendons, our DNA, all of these things in our body naturally lack a center of symmetry and have some level of piezoelectric response. But it wasn't until around kind of the early 2000s that we started to see actually technologically exciting responses. So it wasn't just a scientific curiosity anymore. So one of the kind of foundational groups in this was André Calkin's group in the University of Ecaterinburg and Aveiro in Portugal. And they looked a lot at diphenylaniline motifs, so diphenylaniline crystals, peptide nanotubes, and various kind of nanoscale forms of that peptide to produce very high voltages and very high piezoelectric response. And we had this landmark paper in Nature Nanotech just before I started my PhD. This paper came out where they managed to constrain virus molecules between two electrodes and had a virus-powered energy harvester. So really, really cool. So that's when the field started to take off and get exciting from an application standpoint. So the things that we like about our molecular crystals, and you're going to see lots of images of this, we like that compared to raw materials for ceramics, they're much cheaper, which is great when you're selling these to industry as a new class of material. They have a low dielectric constant, which means we get much higher voltage per unit force than ceramics and a little bit more than polymers. They're relatively quick to grow. They're very moldable, which is what we've recently developed. We can make them into whatever size and shape that we want. And of course, they're eco-friendly. So biocompatible, recyclable, they're non-toxic, and there's no byproducts during their synthesis or their crystallization or their disposal. So the challenges with them is that compared to ceramics, their piezoelectric constants are quite low. So it's a piezoelectric constant D, which is picocoulombs per Newton. So charge per unit force. We're still not hitting the level that ceramics are hitting with that, and I'm going to show you how we're taking on that challenge. We're also learning to control their growth mechanisms. You can look at how these polycrystalline assemblies grow here very chaotically, and this is how we'd model it in our DFT models. And then the third challenge is actually getting these to a point where we can electrode them, package them, put them into devices, put them into those arrays that I showed you, those piezoelectric tiles, and get these out into the world to be used practically. So in terms of what these assemblies look like and why it is challenging to work with them, is that if you take a simple piezoelectric energy harvester here, you'll see this is 2 copper electrodes, and between them you have a polycrystalline film. This is DL-alanine, which is a small racemic amino acid. You can see the chaotic self-assembly. So this is them grown naturally from a saturated solution on the bench. Each of them does have that dipole moment that Jess was talking about, but when you grow them in these massive polycrystalline assemblies, if these dipoles aren't orientated, they start to cancel out. So we're working on growing these in a way where all of the dipoles are at least relatively orientated in a way that maximizes the piezoelectric output of your device. But where we start with our materials is with density functional theory and is with predicting their properties. So what we do for our models is we take our XRD structure, our crystallographic information file, and from that we can predict the full electromechanical spectrum of properties for our materials. So that includes the remnant polarization, Coulomb per meter squared, which is connected to the dipole per unit volume that Jess was talking about. We can predict our dielectric tensor, our elastic stiffness tensor, and then all of the properties that come from the elastic stiffness tensor, the compliance, the Young's modulus, and all of those different properties. So how that led us into this field was when I first developed these models back in 2017, we started to use glycine as a case study. Glycine is polymorphic. One of its polymorphs, alpha-glycine, is centrosymmetric, which makes a nice negative control. Beta-glycine, metastable, in which we discovered a very high piezoelectric response here, that 178 picometers per volt. And that was discovered by our models because of the very low shear stiffness in beta-glycine. So in this study, we had to stabilize this metastable polymorph onto a conductive substrate, and then we did our converse piezoelectric testing, where we passed an electric field through our little slice of crystal, caused it to resonate, and then derived the piezoelectric properties from that. Then the third polymorph of glycine is gamma glycine. And this has really become our benchmark anytime that we're going in for a new application, because gamma glycine crystallizes in a unique space group among a lot of amino acids where it has a natural longitudinal piezoelectric response. Longitudinal means that you can have your electrodes on your material, as I've shown you in the other image, and you can apply your force along the same axis and then get your charge out longitudinally. So it's just the simplest form of device that we can make and the easiest to exploit for applications. So this was our very first amino acid energy harvester that we made here in UL. Just sandwiching our grown crystals kind of in a very ad hoc manner onto our electrodes, tapping them, and then seeing what electricity came out of that. So that was hitting about 0.85 peak-to-peak voltage from gamma glycine back in 2018. But that wasn't enough to discover, I suppose, these materials and then validate their response. The benefit of using density functional theory to calculate properties is that we can then look towards understanding those properties. So we expanded out our models to look at all of the proteinogenic amino acids. We saw that a lot of them had very significant shear piezoelectricity. So that means when you apply a shearing force along a particular axis, you'll get charge out, again, along one of your perpendicular axes. And we saw that this was directly related to the fact that they all crystallized in a monoclinic space group. And the monoclinic angle allowed for that really high kind of fringe or hinge flexibility that would generate a lot of ionic displacement and a lot of voltage out of these materials. That moved us on from piezoelectricity to a lot of collaborative work looking at different functional molecular properties. This is a collaboration with Sam Khan and the group in Aria University, where we looked at photosalience, because again, photosalience generally is due to a huge buildup of stress in the crystal. So we can track our anisotropic stiffness, when a certain crystal is getting irradiated under UV light, while it is undergoing this photosalient process, and then the single crystal to single crystal transformation that happens during that process. And we extensively benchmark all of our models because we try to be very quantitative in our predictions. And you can see just from this study that example of the high predictability versus nano indentation for that study. Then going on to ferroelectricity. This is a study with Professor Bhumi-Shankar's group, where we looked at quite a large ferroelectric molecular crystal. We could look at, again, the remnant polarization in different directions. We could also in silico calculate our stress strain curve and look at our elastic and plastic region to determine how much ionic displacement would take place. And again, look at what the actual bonding patterns and supramolecular packing tells us about piezo and ferroelectricity in these materials. So we were able to directly relate our single crystal density functional theory models to the macroscopic polycrystalline devices that the guys were making and measuring the output electricity from. Then the absolutely kind of top level discovery stuff that we've been developing for a while. On the left, you see, this is by my colleague Pierre Casad here in UL, this amazing model. It's about 1.2 million atoms. It's 4 protein molecules crystallized in a monoclinic space group. The computational expense of this, I thank our national supercomputer for being able to predict the piezoelectric properties of it. But the biggest thing we've ever run is this protein here. We get excellent matching for both longitudinal and shear piezoelectricity versus PFM measurements, which is an AFM technique to measure piezoelectricity. And what we've been developing more recently, as I mentioned, is this in silico stress strain curve, where again, once we have an XRD structure, high resolution XRD structure, we can fully predict using static, low computational expense calculations, the full dynamic stress strain curve of a molecular crystal. And because we know that, again, you get more and more charge buildup as you apply more and more force, we can also track how the dipole moment develops in our crystal with increasing force over various regions. So just 2 kind of different cool things that we've developed for if you have anything from an amino acid crystal all the way up to a protein crystal, which is also solvated, we can get very high accuracy for piezoelectric predictions. And that brings us to the point that we're at now, which is looking at this from a crystal engineering perspective. So I show this not to show off my JAX cover, but to show the actual image of this crystal engineering principle, where we're getting to the point now where we can say, what molecule do we want? What charge does it need to have? Do we want ions? Do we want ligands? Do we want a co-crystal? And how this actually builds up from a self-assembly perspective to form different packing patterns that give rise to particular electromechanical properties. So we're at the Willy Wonka chocolate factory right now of developing molecular piezoelectric materials, which is really cool. This particular study was also fun because it was our first metal organic framework study, and we used our DFT models to validate what our collaborators saw, which was that if you have a MOF where you can switch the guest solvent, then the dipole moment of the solvent, if it's orientated in the correct way, can modulate the piezoelectric response for the same ligand, the same MOF with the same ion. So really lovely, where we show that acetonitrile, because of its dipole moment, maximize the piezoelectricity while keeping the chemistry of the metal organic framework itself constant. So really fun bit of crystal engineering there. And that brings me to literally where we are this week, waiting for our preprint to come out. Because as Suggest pointed out, until now, we have had very kind of independent ad hoc studies on the properties of piezoelectricity in molecular crystals, which has prevented us from making meaningful statistical estimations of structure property relationships and what gives rise to these electromechanical properties. So my fantastic group members, Shubham, Gitu, Rob, and Pierre, have put together this crystal DFT database. We currently have 572 molecular crystals, but we're going to be adding to this for as many years as we possibly can. It's going to be a completely open access resource for the community. So if you're a person here who's doing DFT, we'd love for you to come in and validate some of these calculations and have statistics on that. If you're a crystallographer, we'd love for you to start looking through this database, finding cool crystals with high piezoelectricity, growing and validating them. That's also what we're going to be doing in our group. But it allows us to see this full spectrum of properties for the first time, which is really cool. So across 600 crystals, we can see where the polarization falls. This positive and negative sign is just because it's charged, so we can have positive and negative polarization in our system. So the average falls around 0, but don't worry, the average is not 0. So we have our pluses and minuses on either side. We have every direction that you can have that response in. We can look at longitudinal piezoelectricity, shear piezoelectricity, and then our stiffness. So even for looking at flexible crystals and mechanically interesting properties, you can also see the distribution now across the wide range of chemistries, again, in both longitudinal and shear stiffness. So we're excited to launch this. I was hoping the link would be out today. It's not yet, but any day now, there will be a preprint out with all of this data, with the link to the database for people to check out and investigate. And we're really excited to get feedback on that from the community in preprint form as it goes through peer review as well. And again, what we can do with that data is, firstly, we can, for the crystals that there are experimental data on, we can benchmark the calculations that we're running. And then what Shubham has developed is also these scripts for looking at the chemistry of the database and then correlating that to the various functional groups that are in our crystals. So you can, for these two, these are the total number of crystals that we screened is our first bar. Then when we did all of our checks and balances on what are realistic, sensible structures and properties, we get our second blue line here. And that's the number of crystals that have this particular functional group. And then the red bar is how many of those crystals have a piezoelectric constant of greater than 10 picocoulomb per Newton. So we've seen things like hydroxylation on the small scale in increasing piezoelectricity, but now we can actually see the statistics on how certain functional groups give this property. And obviously there's a lot more work to be done on breaking down which of these are just kind of common structural features of the molecules and which contribute to the bonding patterns that give rise to this property. So this is just step one in what's going to be hopefully a very lovely community resource of as many crystals as we can get to understand these properties. So that's the DFT side. That's as far as we are on that. The second challenge that I proposed was that this way of controlling the growth mechanisms of these materials. So again, back in 2017, 2018, we were just seeing how these grow naturally. So this is 3 different amino acids. This is L-threonine, this is L-alanine, this is hydroxy-L-proline. And we showed that we can get these crystals to cohesively grow together in the same way that a polycrystalline ceramic would look under a microscope. But at this stage, you can see there's warpage, you can see there's gaps, you can see everything is going in every direction. So we could see that they could grow in this way. We could see that they were demonstrating piezoelectricity in using the same mechanisms as piezoelectric ceramics, which was very exciting. But a lot of work had to be done to control this growth. So this is work that my PhD student Krishna has been doing in our group. She has, in the past 3 years, gone from this very sparse, low-density crystallization onto a bottom electrode. By controlling just our simple crystallization parameters, our temperature at which we're carrying out our supersaturation at, layering, which you can see is still a bit messy, but we were talking about if you deposit more solution onto a solid state crystallized assembly, does that increase the density? And then by optimizing lots of parameters, we get this lovely, this is like textbook what we're looking for device applications. So a continuous, dense, semi-orientated at this point, polycrystalline film. It completely covers that bottom electrode. That means that we can place a top electrode on top of it without shorting and then turn it into a device for energy harvesting applications. So this was with L-alanine, but Krishna has gone on to do this for a number of different chemistries, and also, as you'll see, develop them without a substrate at all, which is also cool. So we went from using those conductive substrates, which allowed us to optimize the conditions for crystallization for this material. And then we wanted to get rid of the substrate altogether. Because if we're specifically taking on ceramics, We need to be able to grow molecular crystals in any shape, any size, any thickness, particularly at the macro scale. So one of the big goals of our ERC grant was this level of versatility, that no matter the chemistry of the molecule, that you could crystallize it in whatever shape and dimensions that you want. So this paper just came out over the summer, where we could show that for normal crystallization conditions, you can mold the shape of these assemblies, which then allows you to do things like coat them, electrode them, and use them for applications. Because if we want to phase out ceramics, we have to get to the point where you can just essentially take out the PZT element out of whatever device application and perfectly replace it with this molecular crystal alternative. And all of these showed a measurable piezoelectric response as well without poling. So for ceramics, we need to apply a really high electric field to align the dipoles to maximize the response. But once we semi-orientate our crystals in our assembly, we don't need to pole them because of that naturally occurring dipole. So under the SEM, this is what they look like. If you've seen a ceramic under an SEM as well, you'll see that these do look quite similar, which is also exciting. We like to see on the surface this kind of molded morphology more, because if you have what are essentially many, many single crystals that have very defined boundaries, that's going to give you a very brittle polycrystalline assembly. So we like to see some level of this kind of messier molded assembly at the surface, just because it creates that cohesiveness that you need to make this mechanically stable. So we can control this with the concentration of our solution, or increase or decrease the density of the materials. And then when we got to that stage, we could do our energy harvesting tests, we could measure our voltage output, our capacitance. So each of these would be a little tapping force on the surface of your crystal, generating a kind of LED light up targets as our 1.2 peak to peak voltage. And for very low piezoelectric response, which is what makes molecular crystals so exciting. That low dielectric constant does so much heavy lifting. So for a material that you might normally not study, because it only has a response of 1 compared to PZT, which has a response of 2 to 500, the dielectric constant actually makes up for that imbalance. So when we're doing energy harvesting, you're actually getting these G33 figures of merit that match or exceed ceramics very naturally without any post-processing, which is very cool. And where we get then is we have our DFT screening, where we can identify interesting candidates with high properties. We have our growth processes, where we can grow these as these macro scale rigid polycrystalline assemblies. And now we have our device and application testing, where we can move them forward for our energy harvesting testing. So this is an example led by Suman Bhattacharya, who's a postdoc in my group, where he discovered this mandelic acid lysine co-crystal that had that longitudinal piezoelectricity that I mentioned before. And that, again, we were able to mold into this macro scale disc. The crystals in this case, they weren't perfectly orientated along the longitudinal axis that we wanted, but the way they naturally self-assembled, so if you can imagine your top electrode here along the surface, your bottom electrode here, and this crystal orientated at 90 degrees, that allows us to actually get out shear piezoelectricity. And because molecular crystals tend to have high shear stiffness, this was a lovely serendipitous, almost accident, where we were able to harness that shear piezoelectricity, but in that really easy longitudinal configuration because of how the crystals assembled. So you can see the surface here blends out into all of these kind of plate crystals. They're a bit thicker than needles that morph together to allow us to harvest unique properties. And then finally, this is where I'm going to finish, is the final challenge with these is, of course, if you've grown a molecular crystal, I would say 6, 7, 8 times out of 10, you're going to be growing it in water. That means that your crystals, when you grow them, are water soluble. And for any application, but particularly some of the stuff we do around structural health monitoring, leak detection in pipes, medical devices and urology, there's a lot of water around. So we also needed to develop a standardized methodology for coating these discs and plates in order to make them, again, viable for technology. So this is work done by Tara in my group on the co-crystal that you saw on the previous slide, where we were able to take apart various pieces of that assembly, show that the piezoelectricity was consistent throughout, and then we were able to coat both those pieces and the entire disc in a low dielectric polymer. That polymer increased the Young's modulus and the ultimate tensile strength of the material, but most importantly, prevented it from dissolving. So if you put one of those co-crystal discs, I think this is actually glycine again. So if you put one of those discs into your beaker of water, after about 10 minutes, this is all that's going to be left of it. But when we coat our crystal assemblies in our low dielectric polymer, low dielectric so that we don't decrease the piezoelectric response, you can see that it lasts for as long as it needs to in those high humidity or literally submerged in water applications. So that was great work done by Tara to achieve this, again, protocol for this workflow of molecular crystal piezoelectric devices. So to conclude, just to really, I suppose, shout out to the crystal engineering community that it's a really exciting time to be working on molecular piezoelectrics. I think we're going to see an explosion of flexible molecular piezoelectrics in the next year. I think we have already, but I think it's really going to explode in the next year and couple of years. And that will really help us to, again, understand those structure property relationships to eliminate any environmentally damaging materials that are currently being used commercially. I showed you some energy harvesting data, but I always like to finish on this study with our collaborators in University College Dublin, where we show, again, gamma glycine polymorph assembly outperforming this widely used commercial polymer PVDF for structural health monitoring applications. So this was a study where we took loads of our electroded glycine sensors, we placed them along the surface of the pipe, and what that then does when there is a leak is the leak causes a vibration. That vibration is detected by the piezoelectric sensor and can alert people to damage in this kind of pipe-based infrastructure. So again, because of the dielectric constant, glycine is very capable of detecting vibrations. Because of our linear electromechanical coupling, the size of the leak will correlate to the size of the vibration, will correlate to the magnitude of the voltage output. So it really helps us to distinguish between different sizes of leaks in pipe states. And we can also do this at the kind of built-in infrastructure level to, again, detect damage early in these kinds of systems. So with that, I would like to thank all of my collaborators. This is my fantastic group here on the right, across the modeling and crystallography and engineering space. Good density functional theory models need some very good experimental collaborators. So I'm eternally grateful to all of the people here who send us fun crystals to model and grow and make devices out of. And you for listening. Thank you so much. I'll take any questions.
Thank you very much for this excellent lecture, which is now open for questions and comments. People are, oh yes. Let me enable Hansbert. Yes, it's still enabled. So the first question comes from Professor Hansbert Birgi. To what extent does atomic motion, ADPs, interfere with your DFT modeling of piezoelectric effects?
Yeah, so all of the calculations that we run, they're static calculations. They're at energy minima at 0 Kelvin. So we try to minimize atomic motion as much as we possibly can. But that means that it's more challenging to relate to experiments where there is a lot more of atomic motion there. So for us, it's about getting a trade-off between DFT, which doesn't allow for much atomic motion, and realistically matching or screening experimental numbers for applications. But a big challenge for us is disorder. We have to do a lot of work when working with the disordered crystals to rebuild them and take into account the relative occupancies before we carry out our modeling.
Mm-hmm. Such as, can you ask your question?
For this very nice lecture. My question is, you mentioned towards the end of your lecture about flexible crystal appearing as piezo. So from this inverse relation between this Cij and Dij, that alone, it makes us think that it. But as an expert in this area, do you think that's a good way to think about it? Elastically flexible crystals. Do we have reasons to expect a exceptionally high piezo response in such materials?
I think so, yeah. I think from an engineering perspective, so your piezoelectric output is your net polarization in your crystal divided by your stiffness. It's quite hard to change the polarization, but from a crystal engineering perspective, it's relatively easy to engineer a flexible elastic crystal. So absolutely, I'd expect them to have, technologically significant output as a class of material. Yeah.
And this, thank you. And the so-called plastic versus elastic materials, how do you see them? Like the in terms of piezoelectric performance, plastically flexible crystals versus elastically flexible crystals.
Yeah, I mean, plastic are interesting. Once you can return back to your equilibrium state, you're just continuing to get more and more charge. So it's once the crystal, the plastic should be more exciting because you're not entering into kind of brittle, bendable crystal areas for that. But you'll have seen there's a gorgeous, was it a Nature paper came out from Udi Gazet's group this year, where they made they combined a flexible, self-healing piezoelectric crystal similar to the work that Malaretti published in 2022. And that was really an amalgamation of all those big discoveries from the past couple of years, where they had a peptide that was piezoelectric that could form into a supramolecular assembly at the macro scale that healed when you broke it in half. So I think all of those properties can come together really synergistically now to create these really cool, multi-faceted crystals.
Okay, thank you. Thank you very much.
Yasser, you can ask your question now.
Thank you so much, Professor. Professor Guerin, thank you very much for the talk. I have two questions.
Mm-hmm.
First one is that I have read some papers that they claim and they tried actually to grow bigger crystal of piezoelectric material, have a better response. Do you think, compare, for example, the fields that you have, the polycrystalline fields, if you can ideally grow a single crystal, that would be better compared to the polycrystalline field?
Yeah, no, that's a great question. Yeah, so your single crystal will always have the higher response than the polycrystalline assembly in the natural state. So say if our DFT predicted value is around 10, polycrystalline assembly generally jumps down to at least kind of 4 or 5, depending on the orientation. But again, that's with that natural chaotic growth that you saw. But what we've seen with ceramics is that you can have a polycrystalline assembly that has a value of 70 picocoulomb per Newton. If you pole that, that's how you get your 300 to 500 picocoulomb per Newton. So I think the only way your polycrystalline could surpass your single crystal is if you do some kind of electric field based deposition, which some people are working on, where you're applying an electric field during your crystal growth, or post processing, where you're just doing it like a ceramic, applying an electric field and orientation.
Exactly. Because so then all of the polycrystals, they are in a similar direction.
Yeah, exactly.
And as a second, thank you. And I guess as a second question, you mentioned in some of your slides that you predicted the piezoelectric response, or actually the coefficient. So what is the method that you use? Because there are many different things.
Yeah. So we use VASP, which is a DFT software. So it's density functional perturbation theory is what we use to get polarization and dielectric. And then finite difference method is how we get our elastic stiffness. There's also methods within, so VASP is just annoying because you need a license for it, but CP2K is a great open access software for calculating this. Crystal is another great software that can calculate these tensors. Once you've benchmarked against, zinc oxide or some small crystal with known properties, then you have the workflow for using it on a molecular crystal.
Okay, perfect. Thank you so much.
Thank you. Piero, I can read it, or you can ask question yourself. You are on. If you enable your mic.
Yes, can you hear me?
Yeah.
Well, the question is really easy. You have chosen the amino acid glycine, which is the only one which is not chiral in reality, and so it does not guarantee you to go into piezoelectric crystal structure. And glycine is known at least in 3 different polymorphs, one of which is centrosymmetric, the alpha form. The question is, how isn't that a bit dangerous that you may try to deposit this one, and maybe you may have the risk to deposit the alpha form, which of course will not be efficient for your purpose. What was the reason to choose glycine in this respect instead of another amino acid?
Yeah, I mean, the challenge with polycrystalline is, generally, if you look at every single crystallite in that, it's probably going to be mixed phase. But the way that we control the polymorphs is for beta, you want to grow it in the presence of an alcohol. And for gamma, you want to grow it in the presence of a salt. So great work has been done before us on controlling polymorph growth of gamma glycine by a very precise ratio of salt to glycine in your supersaturation solution.
Okay, but in terms of permittivity, is glycine guaranteeing you something better than, for example, alanine?
Ooh, no, the permittivity will always be the same. We use glycine as our first benchmark because of that longitudinal piezoelectricity. Thankfully now with the database, we can look at other non-polymorphic materials that have that longitudinal piezoelectricity, but until recently, it was the only, I suppose, common, low-cost, easy-to-grow crystal that had that D33 response.
Okay, so it's fabrication basically the guideline for you. Yeah. I mean, easier fabrication means less cost also in producing the material.
And that it's the specific space group for gamma glycine is very rare. So gamma glycine, DL-alanine were the only two back in kind of 2020 that we could grow that had that space group that allowed for that particular response.
Okay, thank you.
It was a really nice presentation, Professor Guerin. I have one question. In your work involving molded biomolecular assemblers, why does gamma glycine plates show a maximum response at a particular thickness, which was even greater than longitudinal value of a single crystal?
Yeah, so there's two properties there. So the D constant, the D33 of gamma glycine is in and around 10 picocoulombs per Newton. But the values, I think I'm still sharing, I am, yeah. So the values that I showed for gamma glycine were G33s. So it's volt per unit area and per unit force. So for this, we see a change because of the capacitance. So the bulk properties of the material aren't changing, but if you have a different thickness of plate, you'll have a different capacitance, which will give you a different voltage output. And that's what this G33 value is telling you. So your single crystal would have a much higher G33 than that in that configuration.
Okay, thank you very much. The next question comes from Vikas. I do not know who is hiding behind this this link, so but you can ask question yourself if you want to. It is, if not, then let us read it. It is mentioned in one of your slides that gamma glycine crystal generate high piezoelectric because of low dielectric constant. Is this helpful in every case?
Yeah, so it's helpful in every case for energy harvesting. So just to be careful about distinguishing piezoelectric response versus piezoelectric voltage. So your molecular crystal might have a low piezoelectric response, but that dielectric constant means that generally you will always get a high piezoelectric voltage out of that material. So yes. Yeah.
Okay, Hans-Bert, if you want to, you can ask question yourself.
What about using crystal growth additives to optimize crystal shape for the formation of your final mesoscopic product?
Yes, that's a great idea. I have a postdoctoral researcher who's currently working on that for a particular type of growth technique. Yeah, so if we can control the morphology in a way like that 45-degree angle assembly I showed, yeah, you can absolutely get better orientation and a higher response. Yeah, so that's in the works.
Thank you.
Thank you.
Thank you. Can you obtain any morphology you assume you want to obtain? I mean, is this at this level that you can get what you want to?
I suppose it's that we can screen it now. So if we have our DFT predictions, then we can do our kind of BFDH morphology prediction. Then yeah, before you grow your crystal, you can identify a morphology that we know will assemble in a nice way for this Disker plate application. And then yeah, pick the chemistry that will embed a particular electromechanical response.
I must say that I like very much your idea of data bank of the theoretical property, piezoelectric properties. And do you have also a sub-base of experimental results? I mean, they should go together. I mean, it would be great to have everything in one place.
Yeah, absolutely. So what we're going to start doing is, yeah, anything that there's existing literature data on, we're going to start adding in. So we have a little, page for each crystal that will have any experimental data. And then we'd like there to be a feature where people can upload any experimental validation they do with their own literature as it continues to develop. Yeah.
Thank you very much. Are there any more questions, comments? Somebody is typing in.
Is related to this data bank where you have nearly 600 structures.
Yep.
So did you calculate the piezoelectric coefficients at the same level as you did for gamma and beta glycine? It should be a very expensive business, right? I mean,
yeah. So we started with, so we've categories that we're working through. So these 600 are the smallest crystals that met the criteria for this. So they're all 50 atoms or less in the unit cell. So we went with the biggest bang for our buck computationally to start with, and now we're going to bigger and bigger unit cell sizes. But yeah, as I said, a huge shout out to our national supercomputer who lets us do these things. Yeah.
Okay, very interesting. Thank you.
So we have next questions from Vikas. Madam, higher is the electric constant, higher will be capacitance, which will lead to higher storage charge in capacitors. So, but here in the case of piezoelectric, it seems different. Why?
Yeah, so I mean, yeah, it's the physics of it. So your charge storage in your dielectric will be distinct from your charge generation in your polar dielectric. So you're correct in that your higher dielectric will generally, depending on thickness, have that relationship. But for piezoelectricity, it's about how the surface charge that's generated on the surface of your crystal with each pulse can then go in to be stored in the capacitor. So to distinguish between what's collecting the charge and what's generating the charge is what the dielectric constant affects.
Are there any more questions? The last chance. As I do not see any more questions, Sarah suggests, thank you very much for this beautiful lectures and for very interesting discussion.